Time feels simple. We wake up. The day passes. Night arrives. Seconds turn into minutes. Minutes into years. It feels steady, constant, and universal. But physics tells a very different story. Time is not just a ticking clock. It is not something that exists on its own. Time is part of the structure of the universe itself. To understand what time is, we first need to understand how deeply it is connected to space. Before the 20th century, time was thought to be absolute. It flowed at the same rate everywhere, for everyone. No matter where you were or how fast you moved, time was assumed to be the same. This idea changed completely with Albert Einstein. Einstein showed that space and time are not separate things. They are woven together into a single entity called spacetime. In this framework, time is a dimension, just like length, width, and height. But unlike space, time behaves differently. You can move freely through space. You can walk forward, backward, left, or right. But you can only move forward in time. This difference is one of the deepest mysteries in physics. According to Einstein's theory of relativity, time does not pass at the same rate everywhere. Time slows down near massive objects. Time also slows down for objects moving at very high speeds. This is not an illusion. It has been measured. Atomic clocks on satellites tick slightly faster than clocks on Earth. Clocks on fast-moving airplanes fall behind those on the ground. Time itself is affected by gravity and motion. There is no single universal now that everyone shares. Each observer carries their own time. Despite this flexibility, time still appears to move in one direction. We remember the past. We experience the present. We anticipate the future. We never see broken things reassemble themselves. We never see smoke gather back into a flame. This directionality is known as the arrow of time. But where does it come from? The laws of physics themselves do not seem to care about direction. Most fundamental equations work the same whether time runs forward or backward. A collision between particles can be reversed mathematically without violating the laws. So, if the laws are time-symmetric, why is our experience not? The answer appears to lie in entropy. Entropy is a measure of how many possible arrangements a system can have. Low entropy means order and structure. High entropy means disorder and randomness. The universe began in a very low entropy state. Over time, entropy increases. This is the second law of thermodynamics. Heat spreads out. Energy becomes less useful. Systems move toward equilibrium. This gradual increase in entropy gives time its direction. It explains why we remember the past but not the future. Memories require order. The past was more ordered than the present. As entropy increases, information about exact states is lost. The arrow of time may not be built into the laws of physics themselves. It may emerge from the initial conditions of the universe. This raises a profound question. Why did the universe begin in such a low entropy state? This question remains unanswered. Some theories suggest that time itself emerged from more fundamental processes. In certain approaches to quantum gravity, time is not fundamental at all. At the deepest level, the universe may be timeless. Change exists, but time does not. Time emerges only when systems become complex enough. In this view, time is not something the universe is in. It is something the universe does. Other theories propose that time may be cyclical. In a cyclic universe, the arrow of time could reverse or reset between cosmic phases. Some models suggest multiple arrows of time may exist in different regions. Others propose that the arrow of time is linked to the expansion of space itself. As the universe expands, entropy increases. As entropy increases, time gains direction. If the universe were to stop expanding or begin contracting, the nature of time could change. Black holes add another layer to the mystery. Near a black hole, time slows dramatically. From the outside, an object falling toward a black hole appears to freeze at the event horizon. From the inside, time continues normally. This shows that time is not just subjective but relative. Different observers experience different timelines. At the center of a black hole, our understanding of time completely breaks down. The equations stop working. Quantum mechanics and general relativity disagree. This suggests that our understanding of time is incomplete. Time may behave very differently at the smallest scales. The smallest unit of time we can define is the Planck time. Below this scale, the concept of time may lose meaning altogether. Some theories suggest that space-time itself is made of discrete units. Time may tick in fundamental steps, not continuously. Others suggest time is an illusion created by entanglement and information flow. Even consciousness may play a role in how time is perceived. Our brains create a sense of flow by comparing memories to incoming information. Without memory, there is no sense of time passing. This raises the question of whether time exists independently of observers. Physics suggests yes. Experience suggests otherwise. Time may be both real and emergent, fundamental and constructed. The deeper we look, the more complex the picture becomes. Time is flexible, relative, and deeply tied to entropy, gravity, and the structure of the universe. Yet it remains one of the most familiar aspects of existence. We live inside it. We measure our lives by it. And still, we do not fully understand what it is. Time also plays a central role in cosmology, the study of the universe as a whole. When astronomers look into deep space, they are also looking back in time. Light travels at a finite speed. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. The farther we look, the earlier the universe appears. This makes time an observational tool. The oldest light we can see is the cosmic microwave background. It was released when the universe was about 380,000 years old. Before that moment, the universe was opaque. Light could not travel freely. This marks a boundary in time that we cannot see past using light alone. As we trace the universe backward, density and temperature increase. Eventually, our equations point to an extremely hot, dense state. This is what we call the Big Bang. But the Big Bang was not necessarily the beginning of time. It marks the earliest moment we can currently describe. General relativity suggests that time began there. But quantum theories suggest something more subtle. In some models, time existed before the Big Bang in a different form. In others, time emerged only after the universe cooled and expanded. One influential idea is the block universe. In this view, past, present, and future all exist equally. Time does not flow. Instead, all moments are laid out in a four-dimensional structure. We experience time moving because our consciousness moves through this structure. Physics does not single out a preferred now. Different observers have different slices of time. The block universe aligns well with relativity but challenges our intuition. If the future already exists, what does that mean for free will? Physics does not answer that question directly. Another idea comes from quantum mechanics. At the quantum level, time behaves strangely. Some equations work without time at all. In certain interpretations, the universe evolves not in time, but through correlations. Time emerges when systems become entangled and complex. In this view, time is not fundamental. It is a result of relationships between quantum states. The arrow of time may arise from how information flows and becomes inaccessible. As systems interact, information spreads. Once spread, it cannot be perfectly recovered. This creates irreversibility. Black holes intensify this problem. They appear to destroy information. Hawking radiation suggests black holes slowly evaporate. But what happens to the information that fell in? If information is lost, the arrow of time gains a new foundation. If it is preserved, time may be more symmetric than we think. This problem remains unsolved. Some theories suggest that time itself could end. If the universe reaches maximum entropy, change would cease. This state is called heat death. In a universe at equilibrium, nothing happens. Without change, time may lose meaning. Other theories predict dramatic endings. A big rip could tear space-time apart. A big crunch could reverse expansion. Each scenario raises questions about time's fate. Would time reverse? Would it loop? Would it simply stop? Some physicists consider the possibility of multiple arrows of time. In certain regions, time could flow in opposite directions. In others, time may not exist at all. These ideas remain speculative but mathematically consistent. Closer to everyday experience, time feels deeply connected to causality. Causes precede effects. This ordering is fundamental to how we understand reality. If time were to reverse, causality would break. The universe appears to preserve causal structure. Even in relativity, faster-than-light travel would disrupt cause and effect. This suggests that time's direction is tied to the stability of physical law. Time also shapes biological life. Life depends on energy gradients. These gradients exist because entropy is increasing. Without the arrow of time, metabolism, memory, and evolution would be impossible. Life is a process that runs on time's direction. Even consciousness depends on it. Our awareness stitches moments together into a sense of flow. This flow may be constructed, but it reflects a real asymmetry in the universe. Time is both physical and experiential. It governs the cosmos and the mind. Despite centuries of study, time resists simple definition. It bends, stretches, slows, and speeds up. It may emerge, dissolve, or transform. Yet it remains the framework in which all change occurs. Understanding time may require a new theory that unites gravity and quantum mechanics. Such a theory could reveal whether time is fundamental or derived, whether it had a beginning, whether it can end. Until then, time remains both familiar and mysterious. We live within it, we measure it, we feel it passing, and still it invites deeper questions. Some of the most intriguing questions about time arise when we ask whether it could ever move backward. In everyday experience, time reversal seems impossible. Spilled water does not leap back into a glass. A burned match does not reassemble itself. But at the microscopic level, many physical processes are reversible. The fundamental equations of motion often allow time to run in either direction. This creates a tension between the microscopic world and the macroscopic one. The difference lies again in entropy. While individual particle interactions may be reversible, large collections of particles almost always evolve toward higher entropy. The probability of entropy decreasing spontaneously is extremely small. Not impossible, but so unlikely that it never occurs in practice. This statistical nature gives the arrow of time its stability. Time travel adds another layer to the discussion. In Einstein's theory of general relativity, space-time can curve in extreme ways. Under certain mathematical solutions, space-time can form loops called closed time-like curves. Along such curves, an object could theoretically return to its own past. These solutions appear in rotating universes and near rapidly spinning black holes. However, their physical reality is uncertain. They often require exotic conditions, such as negative energy densities. No evidence suggests such structures exist in nature. Even if time travel were possible, it raises paradoxes. The most famous is the grandfather paradox. If someone traveled back in time and altered the past, contradictions would arise. Some physicists propose that the universe prevents such paradoxes. This idea is known as the chronology protection conjecture. According to this view, the laws of physics forbid time travel that would alter history. Quantum mechanics offers alternative interpretations. In the many-world interpretation, every possible outcome occurs. Time travel to the past would not change your own history, but create a new branch. This avoids paradoxes but introduces other challenges. At present, time travel remains a theoretical curiosity. no experimental evidence supports its feasibility. Another question is whether time could flow differently in other universes. In multiverse theories, different regions may have different physical constants. Some universes might have no arrow of time. Others might experience time symmetrically. Our universe may be special in having a strong, consistent arrow. This may be a requirement for complexity in life. The origin of the arrow of time may ultimately lie in the beginning of the universe. The low entropy state at the Big Bang set the direction. Why that state existed is one of the deepest unanswered questions. Some propose that it was simply a boundary condition. Others suggest it resulted from a previous cosmic phase. In cyclic models, entropy could be diluted or reset between cycles. In eternal inflation, new universes constantly form with fresh initial conditions. Each approach attempts to explain why time has direction. The question of time also intersects with information theory. Information and entropy are closely related. As systems evolve, information becomes spread out and inaccessible. This loss of usable information creates irreversibility. Some physicists argue that time is fundamentally about information flow. Where information can flow, time has meaning. Where it cannot, time dissolves. This idea connects time to computation. The universe itself can be viewed as a kind of information processor. Each moment encodes relationships between physical states. Change updates those relationships. Time tracks that update. This perspective is still developing, but promising. As we explore deeper, it becomes clear that time is not a single concept. It is many layers overlapping. There is coordinate time, measured by clocks. There is thermodynamic time, defined by entropy. There is psychological time, experienced by consciousness. These layers align closely in everyday life, but diverge in extreme conditions. In strong gravity, near absolute zero, or at quantum scales, their differences become clear. Understanding time may require accepting that no single definition captures it fully. Time may be a network of related ideas, not a single entity. This complexity is not a failure of understanding, but a reflection of reality. The universe is subtle. Time is subtle. And as our theories improve, our understanding deepens, but also expands the mystery. Time remains the stage on which all physics plays out. And yet, it may not exist in the way we intuitively believe. It may be emergent, relational, or even illusory. Still, it governs every process we observe. From the life of stars to the thoughts in our minds. In studying time, we are studying change itself. And in understanding change, we come closer to understanding the universe. The question of whether time had a beginning is closely tied to the origin of the universe itself. In our current models, time as we understand it becomes meaningful shortly after the Big Bang. Before that moment, our equations no longer work reliably. General relativity predicts a singularity, a point where density becomes infinite and time appears to begin. But singularities are signs that a theory has reached its limits. They tell us not that nature is infinite, but that our description is incomplete. Quantum theories suggest that the universe may not have begun with a singularity at all. Instead, the early universe may have been governed by quantum fluctuations, where classical ideas of space and time did not yet apply. In some approaches to quantum gravity, time emerges only after the universe reaches a certain size or structure. Before that, there may have been change without time, or a form of time very different from what we experience. This leads to the idea that asking what happened before the Big Bang may be the wrong question. If time itself emerged, then before has no meaning in the usual sense. Other theories allow for time to extend beyond the Big Bang. In bounce models, a previous universe collapsed and then rebounded, carrying time through the transition. In these models, time did not begin, but continued across cosmic phases. In eternal inflation, time may stretch infinitely into the past and future, with new regions of space-time constantly forming. Each model offers a different answer, and none has yet been confirmed. The question of whether time can end is equally profound. If the universe continues expanding forever, entropy will keep increasing. Stars will burn out, galaxies will drift apart. Eventually, all processes that create change may cease. In such a state, time may still exist mathematically, but nothing would happen. Without change, time would lose its physical significance. In other scenarios, the universe could undergo a dramatic transformation. A collapse could compress space-time, altering the nature of time itself. A rip could stretch space-time until even time intervals lose meaning. These ideas remain speculative, but they show that time is not guaranteed to behave forever as it does now. Future discoveries may radically reshape our understanding. A successful theory of quantum gravity could reveal whether time is fundamental or emergent. It could show how time connects to information, entropy, and space-time at the deepest level. New observations may uncover unexpected behavior in the early universe or near black holes. Each step forward brings both answers and new questions. Despite all this uncertainty, time remains one of the most reliable features of experience. We plan, remember, and act within its flow. We measure it with clocks and mark it with calendars. Yet beneath this familiarity lies a rich and subtle structure. Time bends under gravity. It stretches with motion. It gains direction from entropy. It may emerge from deeper principles. Studying time teaches us humility. It reminds us that even the most basic aspects of reality can hide deep complexity. It also connects the smallest scales of physics to the largest scales of the cosmos. From quantum fluctuations to the evolution of galaxies, time weaves everything together. In the end, time is both a mystery and a guide. It shapes the universe and our place within it. And as we continue to explore, time will remain central to our understanding of reality itself, not just as something that passes, but as something that defines what it means for anything to change at all.